Hi, I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics.
Hi, I'm Angela Edwards. I'm a chemistry instructor here at ASU.
So, Angela, we've worked together quite a lot in the past looking at different topics in what I just affectionately call, BioPchem. And of all the different topics I've, looked at, one of the ones that garners the most of the attention oftentimes is looking at ionic strength. And in retrospect, I guess this shouldn't surprise me too much in that it is an incredibly practical, as a chemist or as a biochemist, it's not very, if you're an experimentalist and working with any type of solution at all, especially in biochemistry where you're almost working with aqueous solutions,
Sure.
I mean, ionic strength is one of those kind of baseline things. It's almost as baseline as, what's the pH? What's the ionic strength? It's one of the kind of the core concepts, we look at. And it's one of those few core concepts, like unlike pH, for example, which you would say gets discussed a lot in introductory chemistry. But ionic strength often is not covered at all, in introductory chemistry. And so it's not until kind of more advanced stages, even though it's a concept that can be useful and used in even the most basic aqueous chemistry concepts in laboratory environments. I mean, if you have something biological, one of the first things you ask outside of maybe what is the pH of the solution is what is the ionic strength of a solution, of an aqueous solution of any type of biological system.
Absolutely.
Plays such a critical role in cells, right? Like, what's the ionic strength inside and outside of the cells that drives all sorts of ion movement and stuff. And a lot of times this gets couched in chemical potentials or in other terms or more thermodynamic terms.
Properties in our Gen Chem classes.
Yeah, and in fact, this is actually where, the term came up, and it involves I even brought the book because Lewis and Randall is literally one of my favorite all-time thermodynamic books. In fact, given how it's a very classic old text and was revised by Pitzer and Brewer, and this is kind of the version you can get today, it's still so relevant. I mean, a lot of times, some of the older, more classic thermodynamic texts are just as good and relevant today as they were when they were developed. But Lewis and Randall actually were the ones who came up with ionic strength as a concept when they were looking at activity in solutions and stuff like that when they were developing a lot of the physical chemistry of this. And so oftentimes it isn't until, some type of biophysical chemistry or physical chemistry course, that students will see ionic strength.
Sure. Precipitating proteins. That's when I learned it. It was for purification methods in biochemistry 1.
But it's kind of ironic because if you were, even a high school student or entering college student in any type of lab where you're doing aqueous chemistry, this is a very important thing, to know. So
absolutely.
I'm kind of amazed. Well, in introducing ionic strength, I always find it easy just to introduce it based on, how it was originally defined. And it was defined through an equation that just says the ionic strength of a solution is a measure of the concentrations of the ions that are in that solution. So this is meant to represent the ionic strength. It's equal to, so it's the sum of all the I's for ions. So for each individual ion, whether it's a cation or an anion, we're going to take its concentration of each ith ion. We're going to multiply that by the square of, in a sense, its charge, right? Sure. And why does it have this form? Well, like we said, it's a measure of the concentration, so you can understand why we're going to sum it up, right? That's pretty obvious. We're going to so we're going to take for each ion, we're going to take what its concentration, what its charge squared is. We're going to multiply those two together, and then for each different ion, we're just going to sum all those things together. And then because, like you said, you never, these are typically starting off as, you're dissolving them in solution. So it's never like you're usually dissolving both cations and anions.
Sure,
right?
of course.
And
Charge neutral.
And so, usually we're trying to think, those two kind of, so we're taking the half to kind of indicate, the half that are coming in, that we're going to have equal amount of positive and negative ions.
Exactly. It'll give us the overall kind of charge density of the solution.
Right. And then, also another thing about having opposite charges is the reason for this square, which is, the square is there so that when you square, whether it's positive or negative,
value.
Yeah, you're always going to end up. And so sometimes you will literally see this, kind of written as Z plus, Z minus with an absolute, sign. To me, that's, more or less saying the same thing. And then the last thing I like to say is, because this originally got developed when talking about activity coefficients and understanding aqueous physical chemistry environments of ions and stuff. So oftentimes this concentration, and I've seen it written as an M instead for kind of molarity.
Sure.
But I've seen it written as a B, and usually when they substitute a B or a small m, they're saying the molality instead of the molarity. That can often be confusing, but what I like to say is just, in a dilute limit where everything's behaving ideally, you usually just use molarity. But when you start getting non-ideal behavior, you often need to use molality, the moles per kilogram, to compensate for some of these things because of the volume effect that you can get. Things don't, famously, just because you take 100 mils of water and 100 mils of ethanol doesn't mean you end up with 200 mils of a final volume.
Sure.
Right? You can have non-ideal effects where the volumes change because of the interaction between molecules. And this happens a lot with charge. So oftentimes it's the molality that gets used instead of the molarity.
Molality is also practical because it lets you vary over a range of temperatures, right? So if the density is changing of the solution, then you have a different number of atoms or molecules in the solution. But if you take the molality, then by mass, you have the same number of particles. So it's a really practical measure if you're trying to work in a high or low temperature regime. Same reason that we kind of take the molality for calculating like boiling point elevation, for example.
Right. Yeah, exactly. So that kind of gives us fundamentally what this ionic strength is. And I think it's worth saying, why it's so important, which is, as I've already mentioned, it was kind of developed to help understand kind of activity coefficients. I'd say the one that gets introduced typically most often is something like a Debye-Huckel for, an activity coefficient, to describe, basically, how things can, behave in equilibrium, concentrations, et cetera. But I don't want to focus on that. That's often, the focus in kind of undergraduate level physical chemistry courses, whether it's using something like we have in the past, like a Tinoco book, or kind of an Adkins physical chemistry. But, whether it's even kind of more life sciences or biophysical chemistry relevant, or just straight physical chemistry or electrochemistry, this is a topic that gets covered a lot. But I think, what I like to focus on is that the ionic strength, obviously, it's the number of ions in solution, and it's going to be ion conductivity. So it directly impacts what the conductivity of the solution is. It typically dictates oftentimes rates, rates of reaction, solubilities, et cetera, because the Coulombic force is such a strong one. Because as we learn in, freshman chemistry, ion interactions are kind of at the top of that list, and even ion, dipole interactions, ion molecular. those are some of the strongest because of Coulombic forces. This can really play a huge role in the physical properties and chemical properties, of a solution. So So this kind of shows, typically how things can vary with ionic strength with activity coefficients, which, like I said, gets discussed a lot. But I think sometimes more practical is things like solubility, like how much of something can you get in solution? And it can greatly depend. This is just one kind of biological example of hemoglobin at its isoelectric point. And you can see, like, not only do things vary greatly as a function of their ionic strength, especially kind of initially, as you start changing it initially, but they can also vary by, kind of the type of ion. And this is really, I think, at the heart of it. It kind of makes you go back and remember some freshman chemistry. First of all, it makes you remember, valence, right?
Sure.
Like it makes you remember oxidation number, or, is this going to be a +1? Is it sodium chloride? Sodium +1, magnesium, +2, aluminum +3 type of things. It makes you remember what the charge, in a sense, is going to be on the atom. But it also makes you go back and remember polyatomic ions as well, right? To know that when you see a phosphate, you're not splitting that up into phosphorus and a bunch of oxygens. You're going to take the phosphate and you're going to take its ionic state of that polyatomic anion. And this hints to something that I would say is just by doing a few simple calculations, what you quickly start getting out of ionic strength, which is it really matters a lot whether the ions are monovalent, like sodium and chloride, or whether they're divalent, something like a sulfate, 2- anion, or here where you have magnesium 2+ and sulfate 2-, et cetera, that you get much different effects when you start changing the charge state of these ions.
Right. Yeah. Ionic strength is a really nice measure of the physical behavior of these ions, because you have effects like, for example, if you have 2 valences, then you can have a bridging effect between 2 of these molecules that are dissolved. So you might be able to aggregate them more quickly by binding, 2 of these hemoglobins at some positive charge to the negative charges on the sulfate. So it's going to bridge between those and bring them closer together, so they fall out of solution. So this tells you, again, something about the charge density within the solution, how different ions will affect the behavior of the physical parameters, everything from solubility, viscosity, these kind of properties.
And I think the thing that helps most, and I think we'll probably make a second video where we do nothing but just work a few, there's so many practical problems you can work here. And I think it's just, by working a lot of problems that you really get a quick view. But I think one of the first and quickest ones we can just even quickly look at, I think as a quick example that might help students really solidify some of this. I mean, when I see this, what I immediately remember is, okay, sodium chloride. So, from freshman chemistry, I remember that that's going to be sodium plus ions in solution and chlorine minus ions in solution. And that this is going to be, magnesium 2+ ions in solution and chlorine minus ions in solution. I can immediately get from that the ionic strength of the magnesium chloride is going to be higher. And why do I know that? Because when you start getting divalent cations or anions versus trivalent, the ionic strength keeps going up and up for the same overall concentration of those salts. That's kind of what I immediately remember.
Sure. We would also want to consider the overall concentration of the ion, right? So we have the stoichiometric effect that this one has 2 chlorines.
Yes, yeah,
so it's going to be
makes
100 millimolar for the magnesium and 200 millimolar for the chlorine. That's definitely something that my intro chem students struggle with, is figuring out what would be the total concentration of chloride ions in this solution. Well, we have 100 millimolar contributed from the sodium chloride and 200 millimolar contributed from the magnesium chloride. So we also have twice the concentration just based on the stoichiometry of the chloride in our magnesium chloride. So it's going to be increased by the charge from the magnesium as well as the higher concentration of overall ions. There's 3 ions per formula unit instead of 2 for the magnesium chloride.
Yeah, and like you said, that plays a really big role as well. And so I think this kind of will help point out several things. So like we said, the ionic strength is 1/2, and it's the sum. And I could write it I typically just write an I. I mean, you could write it as, the ith ion till the nth one, and we're going to keep it simple. We're going to do just, since this is already given in kind of molarity, we're going to assume it's lower concentration and ideal. And so it's just going to be, this. So we're going to have, 1/2 out front of all of this, and we're going to take, the concentration of sodium ions. So I think of it as, sometimes you'll even see it written, the concentration of sodium ions, the charge of sodium squared, that's 1 ion, right? And then we're just going to add as many ions as there is, right? So this will be the concentration of chlorine minus, times the charge of chlorine minus squared. And I think you can see so what are you substituting in here? This is going to be, 100 millimolar. What's the charge? It's going to be +1 squared. This is still, like you said, it really does matter how much.
Right.
So this is breaking up into, 100 millimolar sodium plus 100 millimolar of chlorine. So this will be 100 millimolar times -1 squared, and then this whole thing to the 1/2. And I think it's pretty easy to see, the square of these just gets rid of that. You're going to get 200 millimolar, but to the 1/2, and that's what that 1/2 is doing. Right. So in a sense, what our concentration of sodium chloride was our ionic strength.
So this will be true for our monovalent formulas. And anytime that you have a higher charge, then of course you're going to increase both by the effect of the concentration. If you have a monovalent with a divalent, for example, you have more ions, and then the charge will cause them to increase as well. So you can look at some formula unit for a group 1 and group 7 ionic compound and just see the ionic strength by the concentration. But anything else, you're going to have to actually be able to solve for.
Right. And you do get pretty good at just kind of looking at these and knowing, where you're going to end up. So
I think writing the dissociation reactions is critical for students, though.
Yeah,
I think you really want to go ahead and when you see these, write out sodium chloride dissociates into sodium plus and Cl minus. Magnesium chloride will be dissociating to Mg2 plus and 2Cl minus. You need that stoichiometry. I've noticed that even some senior level students have kind of forgotten some of those basics, because
I
spend a lot of time
so
with
in a
just
sense, we
amino acids or whatever
like
recently.
you said, like this one kind of represents the easiest case, right? This is the one everyone starts with. But that said, the most relevant, sodium chloride, saline solutions, the ocean, it's what our own body uses so much, more sodium than anything else, et cetera. But like you said, I think this kind of starts getting at the heart of one of the others. And so like you said, I think it's very important, and you mentioned this, you don't write magnesium chloride like that, right?
Right.
What magnesium chloride is that, and we're going to write it as an aqueous solution. And what is that? What we're going to assume is that at this concentration that it completely dissociates. Now, if it was something like magnesium sulfate, I mean, that's another thing a lot of people forget. that oftentimes that they'll write I've seen physical chemistry books or basic on ionic systems where they'll be like, you have 1 molar of, calcium sulfate in solution and I'm thinking, that much sulfate doesn't go into solution.
In those cases, you need the real concentration.
Or they'll put carbonates or something.
Right. So you would have something in that case, if we have these 2 ions, then remember that this is some equilibrium that has a solubility product, right? So we would have that.
But I think what we would write, knowing some freshman chemistry and 100 millimolar, but you could write it explicitly. If you wanted on a problem to make sure, you could say, my assumption is, complete dissociation.
Right.
Or completely dissolves, in solution. I mean, that's in a sense how you would know in an ionic compound. In this regard, this would probably be, a good assumption.
Sure.
But we're not here to complicate, the problem that way at the moment. But it is one that, oftentimes simple problems have a more complicated solution because people aren't thinking of the overarching thing. Is this really soluble at these levels?
Yeah, you can't just pick any number out of a hat with any salt, right? There's a limit for those things. And you could assume these are equilibrium concentrations. If the problem specified that, regardless of the salt solubility, if you know that you have this equilibrium concentration, then those are the actual ion concentrations as opposed to any solid that you might have. So that might be another wording if you happen to see something that's highly insoluble.
Right. But you would say a lot of times when you see these problems initially, it's just like, you have, calcium sulfate and potassium chloride, each at these, you have a 50 millimolar of this and 100 millimolar of that. What's the ionic strength? They often don't, really. So you would just say, it's never a bad idea to say, I'm assuming these are completely dissociated in solution, even though, but I think you brought up a really good point, and that's why I think it is worth, looking at this. I mean, just in words, they look so much the same, right? Sodium chloride, magnesium chloride. Oh, we already know sodium chloride's ionic strength is exactly its concentration, 100 millimolar. So, like you said, your first thought is, wow, I kind of expect the same for magnesium chloride. And there's even more than one reason that it differs. Like you said, for two that we're looking at once. Once is because they're not all monovalent, like sodium and chlorine was. Chlorine obviously still is. So this is going to change it some because it's changing that Z. But also, like you said, stoichiometrically, that one's going to change it too. Because why? Because if you assume that it's 100 millimolars of this, then that means we have 100 millimolar of magnesium plus 2 ions in solution. But we have 200 millimolar of chlorine anions in solution. And so I think it's worth just quickly reminding students. So we'll write the same equation out. We'll start with, magnesium. So it's going to be the concentration of magnesium 2 plus times Z of magnesium. While obviously this isn't 100% necessary, a lot of people just immediately substitute the concentrations in. I think it's always nice just to write out the sum as all the different ones, that you're doing.
If you want to start with the concentrations, one thing that I will do is I'll just circle the term and write magnesium and circle the next term and write chlorine. And that way I make sure I count for all of them. If you want to save a small step of writing the whole equation twice, at least go and make sure that you counted for all of them, because you'll probably have more than one compound for a calculation on any kind of homework or exam question. So,
and this concentration is still, it's going to be the same as the concentration, dissolved in aqueous solution. But unlike that, this is going to be, plus 2 squared, and then this is going to have there's double the chlorine concentration, so we'll have 200 millimolar here, and then minus 1 squared. Overall, we're going to have 300 millimolar, so significantly higher ionic strength. Why? Well, one was, like you said, the very obvious, which is we have more ions in solution. Chlorine, we have twice as many chlorine ions in solution, but it's more than twice the ionic strength. The other component to why it's higher than just twice is because we have a divalent cation instead of a monovalent. And these higher charged species add ionic strength.
Yeah, we can see that that's much more effective, right? 200 millimolar of that comes from the magnesium. So that one's 4 times the ionic strength of the sodium cation. So the charge is more, just like in your ionization energy, other properties that you learned about when we were looking at, these ionic compounds way back in Gen Chem, the charge is the most the higher effect term because of that squared component.
So hopefully this, I don't know how quick of an example this was, but hopefully the kind of looking at it step by step will give the first premise of doing this. And I think we'll maybe come back with a future video where we just look at what I would call some common, ionic strengths of polyatomic, like some phosphates and carbonates and things that you see both environmentally, biologically, basic chemical, kind of kitchen type chemistry, things, etc.
I think it's worth noting really quick that we calculated separately the ionic strength of these two compounds. If you wanted the total ionic strength of this solution, if they're together, then you need to add those two terms. So we have 100 millimolar from the sodium chloride, right? And we have 300 millimolar from the magnesium chloride. So the total ionic strength of this solution mixed together would be 400 millimolar. We showed you just the independent
instead of saying
effects.
versus,
oh, I see. Versus,
instead of saying versus that, if I said, this plus this, or that I had both of them in solution, is what you're referring to there. Yeah, I was just trying to look at quickly, like why, when you look at two things that almost look the same, how they can vary.
I just mean because it's likely that for any homework or exam problem, they're going to have a mixture of at least two components, is what I've seen.
Well, and that's
in
for very
all
practical reasons. Rarely do you just get pure salt water. I mean, in biological systems, famously, you not only have, sodium chlorides, but you have potassium chlorides. You have not only magnesium, but calcium. Like you often have multiple things, usually have multiple, not just simple monovalent anions like chlorine, but you often have phosphates, sulfates, carbonates, other things, etc. And so oftentimes you will look at kind of very complicated things and add them all together. So you're right. I think that's kind of that next stage, and maybe we'll make a separate video on some of that as well.
All you pre-meds, this is a topic for you. Blood analysis.
Exactly. Well, thanks for taking the time today, and hopefully we'll be able to follow up this soon.